So it's 8 a.m. and we can continue. So in the previous class, we introduced Faraday's law, started introducing Faraday's law, right? No, actually, no. We introduced and now we just need to apply it in several cases. So first of all, let me remind you what Faraday's law describes, right? So if you have a conducting loop, right, which is exposed to some external magnetic field created by something, right? So then, of course, this magnetic field with this loop, we can introduce magnetic flux, right? So there will be some magnetic flux. If that magnetic flux is a constant, then the loop doesn't do anything, right? But if that magnetic flux changes, then current will be produced. Right, that current we call induced current. Of course, EMF will be produced, and as a result, as a consequence, current will start flowing in the loop in a clockwise or counterclockwise direction. Right, and this phenomena cannot be explained by anything except for Faraday's law. That's why Faraday's law was introduced. Right. Okay, there's some activity in the chat. All right, I hope it's not about the quality of the sound. Let me quickly check. Oh, the screen should be fine. Okay. We introduce Faraday's law in this form. EMF equals to the negative rate of change of the magnetic flux. So minus d phi over dt, where phi is the magnetic flux. And that minus in front, it gives us direction of the EMF and direction of the induced current. And dealing with that minus is not very pleasant, not very convenient, right? As a result, when something is not very convenient, of course, sooner or later somebody will come up with a nice rule, right, which can be used instead of something which is not pleasant. Okay, so Lenz introduced his rule, how to handle that minus, right? So we call that rule Lenz rule, right? In order to find direction of the induced current. So after introducing that rule, now we will divide application of the Faraday's law into two steps. First, we will find the magnitude of the EMF, and then we can apply Lenz rule to find the direction, right? Okay, and now let me remind you quickly that Lenz rule. We spent like 10 minutes at the end of the previous lecture discussing Lenz rule, and now let me quickly remind you that. Again, initial situation, the conducting loop exposed to the external magnetic field, right? And there are two situations, right? Of course, there will be flux, magnetic flux, and there are two situations. This flux can grow in time or can die. Because if the flux is constant, then loop will be completely happy and it is not going to do anything and current is not going to be produced if the flux is constant. But if the flux is increasing, then the loop will wake up, right? And start reacting, start responding, right? Because it doesn't like the fact that magnetic flux changes. In this case, it's growing, right? So, and the loop will try to suppress that growing flux. It rebels. I compared it with like that famous character Che Guevara, right? And in which way? It will start producing current, induced current. And of course, in a direction clockwise or counterclockwise, right now we don't know, but we do know that it will pick a direction so that the induced magnetic field, if there is a current, there must be magnetic field, right? So induced magnetic field is in the opposite direction to the direction of the external magnetic field. Right, so you see this marker is up, this marker is down. So within the loop, directions are opposite. Why opposite? Because if this flux is positive, flux produced by the external magnetic field, then flux produced by the induced magnetic field will be negative. As a result, there will be, if you add them up, of course, magnetic flux will be reduced, right? So suppression, right? And you know what? It's sort of funny response of the system, right? Okay, yeah, the system doesn't like that flux grows. And what's the response of the system, right? it starts driving current through itself. It's sort of like a system electrocuting itself, right? In the response, like in trying to be a rebel, and it electrocutes itself. And it's kind of interesting response of the system. But anyway, so now we know the direction of the induced magnetic field. Now external, we don't care about the external magnetic field anymore. Now, once we know the direction of the induced magnetic field, we should be able to find direction of the induced current, because their directions are connected, right? Connected, and we know how to relate them using right-hand rule number 2. Okay, so now, I have to curl my fingers around the wire in such a way so that my fingers, you see directions of my fingers, and direction of this marker is down, will match within the loop, right? So of course I have to position my hand like this, right? And then my thumb, outstretched thumb, gives me direction of the induced current. Of course, if I position my hand like this, okay, direction will be wrong. Marker is down, but my fingers are up, right? So this is the correct position, right? So, and it gives me direction of the induced current. In this case, from your point of view, it will be clockwise direction, right? Okay, so that's when flux is increasing. Now the opposite situation, what if the flux is decreasing in time? Again, the same initial conditions, loop, external magnetic field, but now flux produced by this field is going down. So now again, the loop is not going to like it. It will wake up and start responding. In which way? It will start driving. Okay, first of all, in which way? In this case, the loop will become supportive because the flux is dying, going down. So again, loop is not going to like it. It will try to support it so that the flux will live longer, right? Of course, it will not support that flux forever, right? No, it will just use its limited resources. For some short period of time, there will be some support of that dying flux. But sooner or later, anyway, it will die, right? Okay, so now, and so in which way it is going to respond? It will start driving the current in the proper direction so that the induced magnetic field will be in the same direction as the external magnetic field, because in this case both fluxes are going to be positive and they will add each other, right? So as a result, flux becomes a little bit larger, right? So supports. Okay, so now once we know direction of the induced magnetic field, we don't need external, we can trash it. And again, this magnetic field is produced by the current. Of course, directions are connected by the right-hand rule. So now magnetic field is up, so I have to position my fingers like this so that my fingers within the loop will be also up. And then my thumb gives me direction of the induced current. Again, if I position like this, it will be wrong direction. My fingers are down, but magnetic field is up. And again, within the loop, right? So this is the wrong direction, this is correct one, right? So that will be the correct direction of the induced current. So this is Lenz's rule, right, which we can use to find direction of the induced current. Now a few examples. We're going to look at many examples today, pretty much the whole class of example. Okay, yeah, don't forget about the code, right? Attendance code. So first example, this situation. So let's assume that I have this loop, right? And I have a permanent magnet. And what if I move this permanent magnet into the loop? What will happen in this loop? Are we going to produce current? And what's the direction of the induced current, right? Okay, so that's the situation. And so here the conducting loop, here is my permanent magnet. Well, let's say this is the North Pole, and we move that magnet up, right? Okay, so we need to find the direction of the induced current. In order to do that, we need to first of all find out what happens to the magnetic flux produced by the external magnetic field. First of all, actually, we need to show external magnetic field. And of course, that external magnetic field is produced by this permanent magnet. Okay, let me draw a few magnetic field lines. Okay, I know these magnetic field lines should have a sort of curved shape. I was lazy to draw curved lines, so I just drew straight lines. It's not a big deal, right? Okay, so these are this is our external magnetic field, right? Now, what happens to the magnetic flux produced by this external magnetic field? Again, inside of the flux, there are three parameters: B, magnetic field; A, area of the loop; and the angle between B and A, theta. So three parameters. We need to analyze them all the time. So now let's start analyzing those three parameters. Magnetic field. What happens to the magnetic field, external magnetic field? Of course, it's growing because we're moving the magnet closer and closer. Of course, magnetic field becomes stronger and stronger. Magnetic field through the solenoid or through the loop, right? So magnetic field increases. Area of the loop, we don't do anything with the loop, so area stays the same. And then angle, okay, angle is a little bit more complicated, but of course, strictly speaking, angle will be slightly changing. But let's assume that the angle is constant for simplicity, right? But of course, yeah, angle will be also slightly changing, but let's assume that the angle stays constant. So out of three parameters, only B changes, okay, changing. So as a result, what happens to the flux? Because flux is a BA times cosine of angle between them. Flux is going also increasing. So magnetic flux is going up. Right, again, this arrow up, it means it's growing. Right. Okay, so once we know what happens to the magnetic flux, now we are ready to start applying Lenz's rule. Right. So here a flux is increasing. So what will be a response of the system? It doesn't like it, right? The system, the loop doesn't like it. And of course, in this case, the loop will rebel, right? It will try to suppress the growing flux because it tries to keep the flux as constant as possible, right? So, and here I found some nice photographs or pictures, right? I want you to rebel, right? So it will drive the current in such a direction so that the induced magnetic field within the loop will be in the opposite direction to the direction of the external magnetic field. So, all right, so I can draw these two arrows in the opposite direction, right? It means that B induced is in the opposite direction to the direction of the external magnetic field, right? Okay, so now we know direction of the induced magnetic field, right? Let me also draw magnetic field lines of the induced magnetic field, right? Around this wire. Okay, it's something like this. Of course, I drew a circle, but of course, this circle should be really, really distorted, but difficult to draw a distorted circle, so I just drew a circle, right? Like if this was this infinitely long straight wire, right? But the major point that within the loop, for example, over here, right? So you see, direction of the external magnetic field up, direction of the induced magnetic field down within the loop. So opposite directions. That's what we wanted. That's the major point, right? Okay, all right. So now, once we know direction of the induced magnetic field, we can apply a right-hand rule to find direction of the induced current. Let me use my loop. So pretty much that's what you see, right? Okay, this side is closer to you. This side is farther away from you, right? So, and we see a direction of the induced magnetic field lines is like this, right? You see, right? So I have to position my hand like this, right? And my outstretched thumb gives me direction of the induced current, right? That's what you see basically, right? So if you look from the top, a current will be this way, which is from your point of view clockwise, right? Okay. As a result, I can show this direction of the induced current. You see, again, if you look from the top, it will be a clockwise direction. Right. So now the last step in this train of thoughts, I induced is in CW direction. And again, in the parentheses, you see, it's if you look from the top. So analyzing this situation, I usually create this train of thoughts all the time carefully because it's so easy to make a mistake, right? Once you flip one of the directions and the result will be completely wrong, right? And I see it quite often on the exam, final exam, because usually I give a problem like this. When students try to skip steps or a step, right? And as a result, the answer is most of the time wrong, right? So that's what I usually do. First, analyze three parameters, B, A, theta, in order to come up with a conclusion about the magnetic flux. And from this point, Lenz's rule. If flux is increasing, system rebels. If flux is dying, system will support it. And then once you know the direction of the induced magnetic field after this point, this direction is going to give you a direction of the induced current using right-hand rule number 2. Okay? So that's the first example. Now let's look at another example, at the second example, and then there will be questions for you, right, so that you can practice. This situation, let's assume that we have an infinitely long straight wire with the current. And that current is decreasing. I don't know, 5 amps, 4 amps, 3 amps. It's going down in time, of course, decreasing. And of course, what about the loop? Here's the loop, circular loop. Of course, it could I could have drawn a rectangular loop or triangular loop as long as it is a conducting loop. Okay, I use the circular loop. Right? Okay, the same question. Are we going to produce induced current over here? And what's the direction of that induced current? Right. Okay. So, first of all, we need to see the external magnetic field, because without external magnetic field, we wouldn't be able to produce anything, right? So the external magnetic field creates all this mass, all these troubles, right? And of course, you see that external magnetic field is produced by this current, right? And we know how we can find the value of the magnetic field and the direction. Direction, right-hand rule number 2. You outstretch your thumb in the direction of the current and curl your fingers around the wire, right? So as a result, above the wire, it will be out of the board dots, right? And of course, below the wire, so magnetic field lines will go into the screen, crosses, bunch of crosses. Of course, if you want to know the magnitude, it's you remember B equals mu naught I current divided by 2 pi r. We used that formula many times. Okay, so that's our external magnetic field, right? Okay, so now we need to look at the flux. What happens to the flux? So we need to look at three parameters, B, A, theta. Let's start with area. Area of the loop. Area of the loop stays the same. So area is constant. So it is not going to produce any changes in the magnetic flux. Angle between magnetic field and the area vector. Okay, at this point, you remember, if you have a surface like this, right? So it's up to you which direction you can use as a direction of the area vector. You can point it into the board, into the screen, or out of the screen area vector. It's up to you. There are no any restrictions. I usually pick it in the direction of the external magnetic field to make that angle 0. Right? If external magnetic field is into the screen, and if area vector into the screen, so they are parallel, the angle between them is 0. That's what I usually do. But of course, if you pick it out, the angle will be pi. Again, nothing wrong with that. Just the value of the angle will be different. But anyway, angle in both cases will be constant. And it doesn't change the magnetic flux. So A is constant, angle is constant. The last parameter, B, magnetic field, external magnetic field is going down because current in the wire is decreasing. Right? So as a result, magnetic field also decreasing. So out of three parameters, B is going down, so the flux is going down. So B external is down, flux is also down. So now once you know what happens to the flux, now we can apply Lenz's rule, right? So now we know what happens to the flux. Flux is dying, so the loop is not going to like it. So now the loop will behave like Florence Nightingale, becomes supportive. It will try to support dying flux, right? In which way? it will start driving the current, induced current, in such a direction so that the induced magnetic field is in the same direction as the external magnetic field within the loop. Again, why within the loop? Because we're trying to support the flux. Flux is within the loop. Okay, so in this case, yeah, I found these pictures, right? So, right, so it becomes supportive, right? And within the loop, induced magnetic field will be in the same direction as the external magnetic field, right? In the previous example, directions were opposite because the flux was growing. Now flux is increasing. So, oh, the flux now is going down, decreasing, right? So the system is supportive now. So it means that now at this point I can draw a bunch of dots, red dots representing induced magnetic field. Oh, a bunch of red crosses, the same direction. Sorry. Of course, red crosses, the same direction, right? External magnetic field into the board, induced magnetic field is into the board, right? Okay, so now once you know direction of the induced magnetic field, again, right-hand rule number 2. Where is my loop? Here is my loop, right? So induced magnetic field is into the board, cross, yeah, into the board. Right? So it means that I need to position my hand like this, right? So that within the loop, you see my fingers into this screen, into the board, because that's the direction of the induced magnetic field. And then you see my outstretched thumb gives me direction of the induced current. Because if I position my hand like this, that's the other option. It's wrong. You see my fingers are out of the screen, although our induced magnetic field is into the screen. So I have to position like this, sort of wrapping the wire. Right. Okay, so this direction, clockwise direction, right? So as a result, yeah, I induced in the clockwise direction. So now I can complete this train of thoughts writing. So I induced has a clockwise direction. Right. Again, as I said, every time I usually try to create the whole this train of thoughts, right, to make sure that I don't make some silly mistakes. Still, it happens, right? Sometimes, right? Okay, so that's the second example. So again, in the previous example, flux was increasing, so the system tried to suppress it. Here, flux was dying, is dying, and the system tries to support it. Okay, so now next will be example for you. Right. This. Okay, let me go back maybe. All right, so it will be something similar, but of course I changed the directions, orientation of the system. So what do we have? Now you see we have a wire, okay, an infinitely long wire with the current. Current goes up, you see, current up. And what happens to that current? Current is increasing now, right? And then there is a loop. And you see now it's not a circular loop, it's a rectangular loop, but it doesn't matter. Current doesn't care if you give it I know, rectangular loop or circular loop or triangular loop or elliptical loop, as long as there is a conducting loop, right? Okay, so now it's a rectangular loop. And so now you need to answer the question. What's the direction of the induced current? If there is an induced current, then what's the direction of the induced current? So 3 options, right? Clockwise, counterclockwise, and no induced current. Again, the poll is in the chat, right? Just scroll it up slightly. Again, it's a question number 1, concept test 1. Right, so don't use the second one. The second will be soon. Right. Okay, give it a try. I'll give you at least 1 minute. So my suggestion again, try to create that train of thoughts by yourself, right? Don't just guess it, because it's just a guessing. It's just a waste of time, right? Okay, let me start the timer. Just give your efforts, right? The best you can. Okay, it looks like number of responses is not growing, so it means that I can discuss this. Okay, so I will, as I said, I will create not exactly, but similar train of thoughts. But first of all, we need to start with figuring out where is external magnetic field, and what's the direction of the external magnetic field. Of course, that field is produced by the wire with the current. And in order to find the direction of the magnetic field, in external magnetic field, again, right-hand rule number 2. Again, direction, outstretch your thumb in the direction of the current and curl your fingers around the wire. So on that side of the wire, magnetic field will be into the board, which is cross, right? And on this side, dots. Yeah, so that's the correct direction. So that's our B external. And of course, what happens to this B field? It's increasing because the current increasing, right? Current is getting stronger. Of course, magnetic field around the wire is getting stronger, right? So now we know information about external magnetic field, which creates all this mess. Now we need to figure out what happens to the magnetic flux produced by this field through our loop. So 3 parameters, B, A, theta. Okay, let me start with A, area. We don't do anything with the area of the loop. Area is constant. Angle will be constant, but again, you can make angle either 0 degrees if you pick area vector into the screen. That's what I usually do. I usually pick it in the direction of the external magnetic field. I usually try to make it 0. But if you pick area vector out, it's still good. But of course, in that case, angle will be a pi or 180 degrees. But anyway, in both cases, it's constant. It is not going to change magnetic flux. So A is constant, angle is constant. Then B. But B is increasing. So B makes magnetic flux change, right? Okay, so as a result, I can write, so since B, external B increasing, so magnetic flux also increasing. So flux changes, definitely there will be induced current in the loop. If flux were constant, in that case, the system would not respond, right? So the loop, right? And the current wouldn't be produced. But since flux changes, in this case increasing, so there will be induced current. So now we need to find the direction of that induced current. So flux increases, it means that the system will try to suppress the growth of that flux. So it rebels. The system will rebel. In which way? Of course, it will start driving the induced current in such a direction so that the induced magnetic field is in the opposite direction to the direction of the external magnetic field within the loop. Because again, you remember, the system tries to suppress the flux. Flux is within the loop. So it means that within the loop, I can draw a bunch of opposite direction, bunch of dots. Yeah, so as I said, it rebels, right? So direction will be opposite, and bunch of dots here, right? So that's my B induced. Okay, and now once you know direction of the induced magnetic field, right? So we should be able to get direction of the current, produce that field using right-hand rule number 2 again. So where is my loop? So I still use circular loop because again, it's the same, right? Circular or rectangular. So induced magnetic field is represented by dots. It means out of the board. Magnetic field is out of the board. So I have to position my fingers like this, right? You see, like that, out of the screen. And my thumb immediately, again, it doesn't matter if you position your hand over here or over there, right? Or over there, it gives you the same result. So fingers out and outstretched thumb gives you direction of the current. So it will be this way, counterclockwise direction. All right, and so let me finish this train of thoughts. Yeah, counterclockwise direction. So, and you see it on the picture also, counterclockwise. And your answer is counterclockwise. Okay, awesome. All right. So now the next question for you. This. Somewhat similar situation, but now again, current is still, you see the wire, current is up, but current stays constant. And magnetic field lines are given. So you see direction of the magnetic field. On this side, it's into the screen. Over here on this side of the wire, it's out of the screen. So you see this blue and green. So they represent external magnetic field. And you see the loop, rectangular loop. And now we just drag that loop down. So the same question, are we going to produce any induced current? And if yes, then what's the direction? Clockwise, counterclockwise, and option C, no induced current. Give it a try. Okay, so now let me discuss. I see distribution of answers, and actually I like what I see. Okay, again, so now at this point, external magnetic field, we have information about the external magnetic field. We just need to find out what happens to the flux, magnetic flux produced by that external magnetic field. Again, three parameters, B, A, theta. Okay, now we can start with B. B is constant. B is constant, right? Why is it constant? Because you see, we're dragging this loop along the wire. So as you move this loop along the wire, right, parallel to the wire, the magnetic field numbers don't change, right? So at any point of the loop, the value of the magnetic field stays the same with time, right? So B is constant. And because current is also constant, right? Current stays constant, so the value of the magnetic field at any point stays the same. Then area of the loop, we don't change the shape of the loop, we don't do anything with the loop, so area is the same. And then angle also, you can make it 0 or 180 degrees, it's up to you, but in both cases angle is constant. So all three parameters B, A, and theta are constant, so flux doesn't change. So it means that if flux doesn't change, the loop is completely happy, and the loop is not going to do anything. The loop is not going to produce an induced current. So in this case, no induced current. So the answer is C, no induced current. All right? But sort of following up question. What do we have to do? How do we have to move this loop in order to produce current? Without changing the fact that current is constant. Current still constant, but in which direction do we have to move the loop in order to start producing current? We can move, for example, this loop away from the wire, that direction, that way, right? If we start moving that way, what will happen to the value of the magnetic field? It will start getting smaller and smaller through the loop, because you're moving the loop farther and farther away from the wire to the points where magnetic field becomes weaker and weaker and weaker, right? Before, in the previous examples, we didn't move the loop, but we changed the value of the current by changing the value of the we changed the value of the magnetic field by changing the value of the current. Yeah, that's it. But now we keep the current the same. As a result, if you don't move the loop, yeah, of course, magnetic field will be the same. But if I start moving the loop away, so magnetic field becomes weaker, and of course, as a result, flux starts changing, and as a result, the loop will start producing current. Okay, of course, you need to apply Lenz's rule properly in order to get correct direction. But let's assume, for example, I'm just making it up. Let's assume the current will be in a clockwise direction. If I move that way, okay, where's my loop, for example? So I can use my loop. So if I move that way, let's say clockwise direction. But if I start moving closer to the wire, what will happen? Current will be produced, but now, of course, in the opposite direction, counterclockwise, right? So I can, that way clockwise, here counterclockwise, clockwise, counterclockwise, what I'm producing? AC current, right? So if I stand like this and move this loop back and forth, or I will be like a generator, current generator. Of course, very expensive current generator, right? But yeah, so basically what we do in this situation, yeah, I am a current generator, very expensive, and I am converting mechanical energy into the energy of, okay, I'm producing current at yeah, basically, when we had a battery, we convert what? We converted energy of chemical reactions into the electrical form of energy, right? We produced current in electrical form of energy. Now, by doing this, by moving the loop, I convert mechanical form of energy into the electrical form of energy. I can produce current. So you see, we have different conversions. There we have conversion of electrical, no, conversion of energy of chemical reactions into the electrical form of energy. Now it's a mechanical form of energy into the electrical form of energy. Right? Okay, so that's the second question. And now the example. So what about time? Okay, good. So now let me write something on the whiteboard. U-shaped conducting rail, classical example. You can open any book, and this example is discussed in almost every book. So we have this U-shaped conducting rail. So it's conducting, so current can flow, made of metal. Then there is a rod which can be moved, but there is a physical electrical contact over there and over here. So as a result, over here we have sort of like a conducting loop, right? Right. And you see this rod is moved that way with velocity v. And of course, the whole system you see is exposed to external magnetic field. Magnetic field you see crosses into the board. Then what is given? What else is given? So a magnetic field is given, right? This width of the rail is given, L. Then velocity is given. And let's assume that at this particular moment of time, the resistance of this loop is R. Because here, the next moment, the rod will be moved, and of course, resistance will be slightly different, right? Okay, so at this particular moment of time. So we need to find the value of the induced current, the magnitude, and the direction. Or more or less obviously that a flux, in this case, a flux to the loop changes, and of course, induced current will be produced. But anyway, let's discuss in details carefully. So, direct application of the Faraday's law, right? And we can divide, you remember, application of the Faraday's law into two steps. You can find first, for example, magnitude of EMF and then direction, or first direction and then magnitude. It's up to you, right? So I will first find the direction. Let's apply Lenz's rule. All right. So first, let me write what needs to be found. So find I induced, right? And first, let me put a bullet and let's find direction. Direction. Right. So Lenz's rule must be applied. Okay, so we need to find out what happens to the magnetic flux. We need to analyze three parameters, B, A, and theta. Right, so let me write. So B, external, area, and the theta. So what happens to the magnetic field? It's a given number, constant. It doesn't change. It's a uniform magnetic field. So B is constant. Then angle. Angle. Again, it's up to you. So here's the loop, right? And area vector, you can pick either into the board or out of the board. You have freedom. I usually pick in the direction of the external magnetic field, as I said already several times, in order to make this angle 0. So let me pick the area vector this way. So that's my A, into the board. So as a result, this angle is 0, which is, again, constant. Then area, what happens to the area of the loop in time? course, it's increasing because we move this rod that way to the right. Of course, as a result, the area of the loop, this is the loop, increases in time. So A is going up. So increases. So as a result, we can come up with the conclusion about the magnetic flux, that flux, which is B times A times cosine of angle, is growing. Flux, magnetic flux, is growing in time. Okay, so now we've come to the point where we know what happens to the flux. As a result, flux changes. As a result, current will be produced. And now, what's the correct direction? So now we can start applying Lenz's rule. So flux increases, system rebels, right? It behaves like Che Guevara, trying to suppress the growing flux because it doesn't like the fact that flux, when the flux changes. So it means that B induced will be in the opposite direction to B external. Again, within the loop. So it rebels. Okay, maybe I write underneath. So it rebels, right? Sort of simple word explanation. So opposite direction, so it means over here within the loop, I can draw a bunch of dots representing induced magnetic field. Okay, let me draw a few. So these over here, also I can draw a few, right? So that's my B induced, right? Okay, and the last step, once we know the direction of the induced magnetic field, we can come up with the direction of the induced current, which produces this induced magnetic field. So where's my loop? There is my loop. So induced magnetic field dot is out of the screen. So I have to position my fingers like this, you see, in order to match that direction. So, and as a result, my thumb gives me a direction of the induced current. So it will be, from our point of view, counterclockwise direction. So it will be this direction. So that's I induced. And of course, over here, I can draw the same. So it's I induced. So I induced counterclockwise direction. Again, we apply right-hand rule number 2. Okay, so 50% or maybe 30% of the problem is done. We found direction of the induced current. Right. Now the second part of the Faraday's law. Okay, so it's a first bullet. Now the second bullet, magnitude of V, of current. Magnitude. Right. But of course, before we can find the current, we need to find the value of EMF, because that's what we have in the Faraday's law. EMF equals to minus d phi over dt, right? And now, of course, I'm going to put this jacket, the absolute value, on the sign of d phi over dt, right? Because again, minus gives us a direction. Now we already know the direction, so we can forget about that minus, right? Okay, so minus, of course, I will drop, and I can write, so it will be d over dt, and the value of the flux, it's a B external times A times cosine of angle between them. Angle, I already pick z, or 0. So area vector is into the board, so the angle between external magnetic field and the area vector is 0 degrees, right? So cosine of 0 degrees is just 1. Right? So as a result, I can write absolute value of d over dt, B external times A. Now, look at these two quantities, B external and A. What can you say about B in terms of time? It's constant. It doesn't change. It's given, right? It's a given constant. We have uniform magnetic field. So if it's a constant, of course, we can extract it from the sign of differentiation. But A, no. A changes. A changes in time, right? So that's what we showed over here. So A cannot be extracted, but B, yeah. And moreover, since this is a magnitude of B, this is magnitude of A, of course, all the time they are positive, so we can extract it even out of the sign of the absolute value. So I can write, so it will be B. Okay, you know what? Let me open my explanation box first to tell you that since B external equals to constant. Okay, so now I can make the next step. So it will be B external times the absolute value of dA over dt. Basically the value of the magnetic field times, what is that? Areal velocity, how fast area changes in time. How fast this area changes in time. Okay, at this point, we have to be careful and use one nice trick which allows us to connect what? This areal velocity with this linear velocity. I remember once on the final exam, one student was a very strong student. He got stuck at this point, right? And I remember it took him like 15 minutes to figure out, right, to recall how to handle this situation. So I suggest to do this. In order to make this transition smooth, let's introduce this. Okay, let me use green. Let me introduce this distance. This x, which is basically a distance from this side of the U-shaped rail to the current position of the rod, x, just for a couple of minutes in order to make the transition smooth. And then it will disappear completely. Okay, so let me open this explanation box and tell you. So let's introduce x. Okay, let me finish this example. Just a minute left, 1 minute left. So let's introduce x. As a result, how can you write area of the loop? This distance is x, this distance is L, it's a rectangle, so of course area equals L times x. So area equals to L times x. Okay, that's my explanation box, and now I can go back to my expression. So B external n times d over dt L times x. Now, which parameter out of these two is constant? L. L is constant, right? So L constant, and it can be extracted also from the sign of differentiation. Any constant can be extracted, right? So as a result, we'll get B external times L and times absolute value of dx over dt. What is dx over dt? How fast this x changes in time. It's velocity. It's our, okay, speed, right? Velocity, it's a vector, speed, absolute value of the velocity, right? It's that v, so that's the smooth transition from the areal velocity to this linear velocity. Introduce x, don't forget this, right? So as a result, we'll get B external times L times V, right? So that's EMF, potential difference across the total loop. So now we need to find current, Ohm's law, piece of cake, resistance, we assume that is known at that particular moment of time. So now I induced equals to EMF divided by R equals to, of course, B external times L times V divided by R. So that's the answer. Okay, last sentence. Quite often, when I give a problem similar to this on the exam, lots of students just write BLV. I will never accept it. BLV, it's not some fundamental law. It's just some preliminary result in these calculations. Fundamental result, a fundamental law, it's a Ohm's law, Faraday's law. I want you to start from here and get this. Usually, if a student just write BLV, they usually like remembering this formula. Lots of points will be taken away. Again, in physics, right, you need to remember something, some fundamental stuff like Gauss's law, Ampere's law, Faraday's law, but this is not a fundamental stuff. It's impossible to remember everything. And the goal is, if you remember fundamental stuff, you should be able to apply it and get these BLVs in a couple of minutes. Okay, so that's the example. Sorry for holding you longer.